right, my friends, let's take a look at some of these questions here after example 3. We did make a note in the previous video that we didn't get enough 3s. We probably got too few 3s. How many should we have gotten? Okay, so here's where the worlds of experimental and theoretical probabilities collide. And the idea of what I said earlier about over time, you're going to get 1/6 3s. So 30 rolls, 1 out of 6 of the rolls over time should be 3s. So if you roll 30 times, hopefully it makes sense. You would expect 5 3s. And you can think about that two different ways. 5 divided by 30 is 1 out of 6, which is about 17%. Or just out of every 6 rolls. You can count. Out of 6, it's 1. Out of 12, it's 2. Out of 18, it's 3. Out of 24, it's 4. And out of 30, it's 5. How off was our experimental probability from theoretical? And I put how many different ways can we express it? Okay, one way we already did. We only got 7% 3s. We should have gotten 17%. So we said probability was 10% less than it should have been. Another way of doing it is using percentages but not subtracting them, but instead dividing them. Let me see if I can explain. We can take the 2 out of 30 and divide it by what it should have been, which is 1 out of 6, and press enter. The result you get, 40%, 0.4, means that the result we got was only 40% of what it should have been. So this is a different percent measuring a different offness. The 10% I measured earlier said it's 10% less than it should be. That is simply subtraction. This one is division. I'm saying that the 1 out of 15 is only 40% of what it should be. Let's just, to drive that point home, let's just suppose we actually saw 5 out of 30 3s. Well, if you divide 5/30ths by 1/6, you get 1, because that's 100% of what you should have gotten. What if we only got 4 out of 30? Well, that's only 80% of what we should have gotten. And you can think about that a couple different ways, right? You're down a 3. We should have gotten 5. We only got 4. That's down 20%, which means it's 80%. What if we only gotten 3? Now it's going to be 60%. We only got 2, though. So we only got 40% of what we should have gotten. That's another way to measure offness. There's a third way called percent error. I'm not going to get into because we don't really use it very much in Stats 243. And I'm going to stop talking about that right now just because I just want to plant the seeds for that. We're going to measure offness, as I said, as we go through this course together. Since we got too few 3s, we must have gotten too many of other results. Okay, let's go back and look. Well, the obvious one is 1. 1, 2, 3, 4, 5, 6. Yeah, we got 7 1s. 7 1s. That's way too many. Well, I shouldn't say it's way too many. It's what is it? It's 40% too many because we got 2 where we should have got 7 where we should have gotten 5. Looks like there's a lot of 6s. 1, 2, 3, 4, 5, 6. Yeah, we got too many 6s as well. So anyway, there's a couple ones you could pick for that one. But we only rolled 30 times, which is right. We only rolled 30 times. It's a pretty small sample. So I did run just about 5 minutes ago and built a simulator, which we're going to come back to and show you a video of in a second, that rolls a die thousands of times. And like I said, the next video after this one, I'll show you that thing working. And here are the results I got. So for this simulator, we're going to figure out the chance it rolled a 1, 2, 3, 4, 5, or 6. The first thing I have to do is I got to figure out how many times did I roll this simulator. So I got to add up all those numbers. 1009 plus 1016 plus 1086 plus 1062 plus 1094 plus 1031. And I got 6,298. Let me check the numbers one more time. Okay, good. So 6,298 trials. Here they are if you want to see them. Drag them over so you can see my work. Okay, now the experimental chance that it rolled a 1, because that's what it really is, right? It's an experimental chance. We're not actually looking at the die and counting the sides. We're watching the behavior of the die and seeing what happens. I'm going to put experimental in each of these, and then we're going to do that. All right, so we know that we rolled 6,298 times. So what I have to do is I have to take each of these numbers and divide it by that, and that's going to be my my percentages. So I'm going to do this kind of in a goofy way just to get the numbers for us. I'm going to take each of the numbers and divide them by the sum of all the numbers. And the reason I'm going to do this is so I can do them one by one in the Google window here and then erase and change. So the chance of rolling a 1 is about 16%. And there's absolutely no reason to call that a fraction. You can call it a decimal if you want, 0.16. That's 16%. Now I'm going to change this to 1016. This is the chance of rolling a 2. 16.1%. So the last one was 16.0%. This one is 16.1% if you're feeling saucy. The next one, 1086. This is 17.2%. Fun. That's a chance of rolling a 3. What's the chance of rolling a 4? 1062. That's 16.9%. So they're all pretty quote unquote close to about 16.7%, but they're up and down a little bit. 1094 divided by the total is 17.4%. And you can see so far that's the largest probability because it had the most trials. And last but not least, 1031, 16.4%. So those are the 6 results for right here. All right, now I mentioned the simulator, and I'm going to throw a video explaining the simulator and showing what actually happens when I run it and how it compares to the theoreticals.